Let's jump right in. Welcome to this Info Now Explainer. Today, we're diving deep into the actual gritty mechanics, the hidden historical layers, and, maybe most importantly, the algorithmic future of battery infrastructure. We're literally peeling back the surface of electrochemical energy storage. It's a wild story, right? One that takes us all the way from ancient terracotta artifacts to these massive, digitized megagrids we rely on today. We're not just going to sit here and talk about basic batteries. No, we're looking at the gears, the chemistry, and the real digital processes that keep our modern world spinning. Now, here's a question for you. Why did humanity possess the secret to continuous power over 2,000 years ago, but completely failed to use it? Back in 1938, an archaeologist named Wilhelm Koenig dug up these terracotta jars near Baghdad, dating back over 2 millennia. Inside, just a copper cylinder and an iron rod. But when modern researchers reconstructed this Baghdad battery and poured in an acidic electrolyte, like just basic vinegar, it actually generated a measurable electric potential, somewhere between zero point 0.5 and 1.1 volts. That is a massive curiosity gap. It represents this huge missed principle in human history. I mean, we literally had the secret to continuous power sitting right there in a jar. But the mechanical logic and the industrial need just weren't there yet to actually use it.
Which brings us to Chapter 1, the messy origins and industrial scaling. Fast forward to 1800. Alessandro Volta proved that electricity didn't come from biological animal electricity like Luigi Galvano originally thought, but actually from the contact of dissimilar metals. Volta created the voltaic pile by stacking alternating disks of zinc and copper separated by cloth soaked in brine. But look, I'm not going to sugarcoat the reality here. This was incredibly messy. The sheer physical weight of this heavy stack pressed down so hard that it literally squeezed the brine right out of the lower separators. This caused rapid short circuits, and hydrogen bubbles just choked the copper disks. So yeah, it was a groundbreaking invention that proved electricity could be generated chemically, but structurally, total logistical nightmare. But then, in 1836, the Daniel cell fixed a lot of that. It used a porous earthenware pot to keep the chemicals separated, which finally stabilized the voltage. And that stabilization, that's what actually powered the global telegraph network. We're talking our very first global communications grid, but you couldn't exactly carry a sloshing glass jar around in your pocket, right? Enter Carl Gassner in 1886. He replaced that spilling liquid with a solid plaster paste, giving us the first true dry cell. By eliminating the slosh, this one mechanical shift single-handedly unleashed the consumer electronics revolution. It started simply with the flashlight, but it forever changed how humanity interacted with portable energy. All right, let's move to Chapter 2, the intercalation era and the lithium paradigm.
So, the oil crises of the 1970s triggered an intense geopolitical push to decouple our energy from fossil fuels. And the chemical chosen for this monumental task? Lithium. Now, the absolutely crucial concept to grasp here is intercalation. Imagine molecular structures as thick, dense layers of cardboard. Got it? Now, imagine thin, semi-transparent sheets of vellum sliding perfectly and seamlessly between those cardboard layers without ripping them or altering them in any way. That is intercalation. It's the mechanical ability to safely trap and release highly explosive chemical energy, in this case, lithium ions, within a host structure over and over again without destroying it. It's brilliant.
But the lithium era was born out of some pretty gritty, dangerous trial and error. Back in 1976, M. Stanley Whittingham created the first rechargeable lithium battery. The reality, though, was honestly terrifying. Microscopic metallic needles called dendrites would literally grow and pierce the battery's internal separator. The results? Violent explosions. Yikes. Then, in 1980, John Goodenough doubled the power using cobalt oxide. But it wasn't until 1985 that Akira Yoshino actually stabilized the whole system. He completely removed the pure metallic lithium, replacing it with petroleum coke, a carbon material that safely intercalated those ions. That brilliant mechanical workaround is what led directly to Sony's 1991 commercialization, essentially birthing the laptop and the smartphone. Today, the industry physically divides its resources between two main heavyweights. On one side, we have NMC, that's nickel, manganese, cobalt. These are your high-performance EV batteries. They have unbelievable gravimetric density, meaning they pack a massive amount of energy into a very light package. The catch? They require expensive, controversial cobalt.
On the other side, we have LFP, lithium iron phosphate. Now, these are heavier, sure, but they are incredibly safe, totally cobalt-free, and they boast a massive cycle life. Because of that, LFP has become the absolute backbone of mass-market electric vehicles and stationary grid storage all around the world. Now for the really futuristic stuff. Chapter 3, the algorithmic grid.
7 megawatt hours. To put that into perspective, that is the capacity of stationary mega batteries housed in massive 20-foot shipping containers. These are definitely not powering your phone. Instead, they act as the absolutely essential physical buffers for our electrical grid. Think about it. Wind and solar power are fundamentally intermittent, so these massive arrays have to step in. They absorb the excess energy when the sun is blazing and instantly deploy it the second a cloud rolls over, preventing the grid from just collapsing. They are literally the shock absorbers of the modern energy transition.
Because of this, batteries have officially transformed from isolated consumer goods into what we call a virtual power plant, or a VPP. We're looking at a transversal macro-scale infrastructure now. A VPP is essentially this decentralized network of millions of electric vehicles and home battery systems, all woven together and managed in real time by algorithms to support the reliability of the grid. It's like a giant interconnected web of energy. And this creates what we can call a self-fulfilling digital process. Here is how it flows. Step 1. AI predicts a power deficit on the grid. Step 2. The algorithm automatically triggers thousands of plugged-in EVs. Step 3. Through vehicle-to-grid, or VTG technology, those cars actually discharge buffer power back into the system to stabilize it. And finally, step 4, the owner is automatically digitally compensated. It is this amazing continuous loop where algorithms are shaping human behavior and grid economics simultaneously. Get a load of this number, $3,300. That is the estimated annual revenue per vehicle by 2026, just for participating in these V2G loops. This is the real aha moment of this explainer right here. An electric vehicle is no longer just a car that takes you from point A to point B. It's an active node in an algorithmic power plant that literally pays you while it's just sitting parked in your garage. How cool is that? Which leads us to our final section, Chapter 4, the circular and solid future. Starting in 2027, the European Union is rolling out a mandatory digital battery passport. Now, this isn't just some boring bureaucracy. It's a digital mechanism forcing a true circular economy. It permanently tracks the battery's life cycle, its state of health, and its carbon footprint. Now, why does this matter to us? Well, because it dramatically reduces the uncertainty for buyers in the second life market. See, an EV battery that drops below 80% capacity is pretty much useless for a car, but it's still perfectly viable for a stationary solar grid, and this passport digitally guarantees its health, keeping it out of a landfill. And that brings us to the really gritty reality of urban mining. We aren't just digging lithium out of the ground anymore. Through a process called green hydrorejuvenation, recycling facilities can take shredded, highly toxic black mass from dead batteries and, in under 12 hours, chemically recover 99% pure precursor materials. 99%. It's an aggressive, highly efficient closed loop that feeds right back into the manufacturing cycle. Let's talk physical limits for a second. When we look at specific energy, we go from lead acid at a heavy, inefficient 40 watt-hours per kilogram to modern liquid lithium-ion at around 300. But the final frontier, the technology completely crushing the physical limits of liquid electrolytes, is solid state, hitting 500 watt-hours per kilogram. To put that into perspective, this is the exact threshold required for long-haul flights. In fact, KTL recently launched a condensed battery, explicitly pushing into the electrification of aviation. We're talking electric airplanes, people. So, what's the mechanical logic behind this? Well, solid-state technology completely replaces the flammable liquid electrolyte with a solid ceramic or sulfide architecture. This means intrinsic safety, basically no explosions if it gets punctured, and it allows for an 80% fast charge in just 10 to 15 minutes. But again, I'm not going to sugarcoat it. The logistics are absolutely brutal. Manufacturing these batteries requires massive, incredibly expensive moisture-free dry rooms. Perfecting that solid-solid interface is a manufacturing nightmare that companies are literally spending billions to solve as we speak. And that brings us to a final, pretty provocative question. If AI algorithms now manage our plugged-in vehicles as a massive, decentralized energy grid, are we really driving cars anymore? Or have we simply become mobile batteries serving a much larger digital machine? It's a profound shift in how we interact with physical infrastructure. Well, Thank you so much for spending your time learning with us today. If you found this explainer into energy storage and the digital processes shaping our world insightful, please hit that like button, comment below with what fact surprised you most, and subscribe to InfoNow for more deep dives into our world's history and future. See you in the next chapter.